Thanks to Brilliant for sponsoring today's video.
Today we're going to talk about a really important result in the study of Fourier analysis and Fourier series known as Parseval's identity. But before we do that, I'd like to recall what a Fourier series is and also kind of motivate where this is coming from. Okay, so I've derived the notion of a Fourier series before, so we'll just jump right into what it is. So if f and g are periodic functions with period 2L, then we can express them as sums of either sines and cosines or complex exponentials. It's actually equivalent. So in other words, f of x can be written as the sum as n goes over all integers of a sub n times the complex exponential e to the I n pi x over L. And in fact, if you've got a function, then you can get those Fourier coefficients, the a sub n, via this integral. So a sub n is 1 over 2L, and then the integral from minus L to L of f of x times that same complex exponential. And for our setup, we're actually going to need two functions that are periodic with period 2L, and they're both expressed via their Fourier series. Okay, so what is maybe not the right, but an interesting way or an illuminating way to think about this? Well, and that is that the set of all of these complex exponentials, so e to the I n pi x over L, as n runs through all integers, so that's doubly infinite, is a basis for the vector space of functions with period 2L. So let's notice over here, each of these functions with period 2L can be expressed as a sum of these complex exponentials with certain weights. So why is basis in quotes in this underline here? Well, that's because a real basis, or the actual definition of a basis, requires it to span the vector space via linear combinations. But linear combinations have in their definition finiteness condition. So in other words, a real basis would require these sums be finite, but over here they're infinite. So that's why I've got basis in quotes here. Okay, so now that we've done that review, let's maybe motivate this Parseval's identity.
If you're looking for a free and easy way to learn more about sequences and series, check out brilliant.org. While watching my videos is a great place to start, you'll get more out of learning by doing, and that's why I highly recommend you sharpen your skills with Brilliant. From math and science to data analysis and computer science, Brilliant offers a wide range of topics that'll have you saying, I never knew learning could be this exciting. What really makes Brilliant shine is its problem-solving approach. You won't just passively absorb information, you'll actively learn through hands-on interactive lessons that challenge your thinking and creativity. Brilliant is available on your phone, tablet, or computer, and Brilliant will support you at every step of the way. No matter what skill level you're at, Brilliant can help you improve. They have an excellent calculus and differential equation sequence that fits right in with the topic of today's video. And if that's not for you, they also have group theory, linear algebra, and courses in computer science and more. Keep your love for learning alive with Brilliant's interactive lessons, perfect for those aged 10 to 110. In fact, I use this for my middle school son to help him stay ahead in math, and he loves it. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/MichaelPenn for a 30-day free trial, and the first 200 people will get 20% off their annual premium subscription. Thanks once again to Brilliant for sponsoring today's video.
So let's say we've got the function f of x over here. So it's got these coefficients a sub n. Well, I'd like to think about this function as a column vector. And this is maybe like a common thing to do anytime you're thinking about maybe a vector space which isn't already the vector space of column vectors. In other words, like Rn or Cn or something, is somehow like use that basis to express them as column vectors. So here, what column vector should I think of f as? Well, notice my basis is infinite, so it should be an infinite column vector. And what I'll do is I'll have certain entries play the role of these e to the I n x's. And so this entry right in the middle will play the role of e to the I 0 pi x. And so since that's playing the role of that, that's where A0 goes. So like I said, this right here is for the entry e to the I 0 times pi times x over L. But that's clearly just the number 1, given that e to the 0 is 1. And then as we move up, those entries will correspond to like e to the I pi x over L, e to the I 2 pi x over L, and so on and so forth. So here we'll have A1, here we'll have A2, and then that's going to keep going up. And so this entry is e to the I pi x over L, and then this next entry is e to the I 2 pi x over L, and then like I said, that's going to go infinitely tall. But then, since this is over all integers, including negative integers, that means I need to go downstairs as well. So I've got this entry right here, a sub minus 1, and that's going to be attached to e to the minus I pi x over L. And so this spot in the column vector is for the coefficient of that complex exponential. And then likewise, we'll have a sub minus 2, and then that'll keep going down. So this right here is for e to the minus 2I pi x over L. Okay, great. So there, we've like somehow expressed f as this column vector. And then we can maybe do the same thing for g. So we won't go through all of the same explanation, but right there in the middle, we've got b0. Above it, we have b1, and then that's going to go up and up and up. Right there below it, we have b sub minus 1, and that's going to go down and down and down. But now that we've got these expressed in terms of column vectors, maybe it's interesting to talk about what sorts of operations do we generally do on column vectors when we're studying vector spaces. And maybe the thing that's universal would be something like the dot product, or more generally the inner product. And it's in fact the inner product we want to look at here because it's a complex vector space. And whenever you have a complex vector space, the dot product doesn't quite give you the types of things that you want to be true. So like, for example, the non-negativity condition is not satisfied. I'll let you look that up if you need to. So let's recall this inner product in a finite dimensional complex vector space. So let's say that V and W are both within Cn. Then we would define the inner product of V and W to be equal to the sum as I goes from 1 to n of Vi times Wi bar. But notice in terms of the dot product, that's just simply the vector V dot product with the vector W bar. Okay, so that's our maybe generalization of the dot product to complex vector spaces. Now that motivates us to look at a similar thing over here. So perhaps we would use the same notation, the inner product of f and g. So I'm just going to put a squiggle here because that seems like it should be, well, defined in the same way that this is defined over here. So it seems like it should be the sum as n goes from, well, over all integers, I should say, of a sub n times b sub n bar. That's mimicking this complex inner product or this dot product with the conjugate. But now that we've got this thing right here, this, by infinite sum, the question that maybe naturally arises is, well, what if we haven't calculated the Fourier series over here and we just know the functions? maybe f of x is x squared, maybe g of x is e to the x. Is there some sort of relation between this sum and the original f and g as functions instead of as this Fourier expansion? Well, and yes, there is, and that is exactly what Parseval's identity tells us. Okay, so let's get that on the board. We'll sketch a proof, and then we'll look at some nice applications. Okay, so here's what Parseval's identity says. It says that sum, which we motivated to be interesting on the last board, you know, via an expression that looked a lot like elementary linear algebra, is in fact equal to 1 over 2 times L times the integral from minus L to L of f times g bar. And so now let's sketch a proof of this. And this is not really that complicated of a proof. And this is really not a super complicated result. But the interesting thing here is it allows us to kind of realize these functions as vector spaces, or maybe put some duality between continuous ideas like functions and what's generally thought of as more discrete ideas like linear algebra. Okay, so anyway, let's get to it. I've written let's see, this is the right-hand side of our goal over on the board here. And now let's simply get started. So this is going to be 1 over 2 times L, and then I'll use these expressions for f and g. And so that's going to give me this double sum. So I have the sum as m and n go over integers. I'll use m for the indexer for my function f, and n as the indexer for my function g. And then next I'll have the integral from minus L up to L of, let's see, it will be an times bn bar. So that's from f times g bar. And then we'll have e to the I times this should be a sub m pi x over L times e to the minus I times n times pi times x over L dx. So there's my bn bar from taking my g bar. And then if I take the conjugate of this complex exponential, it just has the effect of putting a minus sign up there. Okay, so now that really motivates us to look at this integral involving the complex exponential. And in fact, since the a and b's are constants, we can actually bring those out of the integral. So let's do that first. Okay, so there we've got that taken care of. And now, you know, like I said, we're going to look at this integral, which I'm underlining in green. So let's take the integral maybe over here, and we're actually going to calculate this in 2 cases. And that's because something a little bit different happens if m is equal to n. So that being said, let's look at our first case when m is equal to n. So in that case, we get the integral from minus L to L of, well, putting those 2 things together, we'll see that we simply get the number 1 because we have e to the I m minus n times pi x over L, but m minus n is 0 if m is equal to n. So that just gives us a dx here, but that's going to give us 2 times L just by simple integration. Notice in the end that 2 times L is going to cancel this 2 times L here, but we're not quite there yet. Okay. So next up, let's move on to the next case, which is the case when m is not equal to n. Okay, so in that case, we're going to have the integral from minus L to L of e to the I, and then m minus n times pi times x over L dx. Well, technically we had that above as well, but the m minus n was 0. But now the m minus n is not 0, which means we shouldn't be afraid to divide by m minus n. So we'll calculate this simply using the fundamental theorem of calculus. So the antiderivative via the chain rule will give us a minus I, and then times an L over m minus n times pi, And then we'll have our function, which is e to the I m minus n times pi times x over L. We need to evaluate that from minus L up to plus L. And now let's introduce some notation just to make everything a little bit simpler. Let's put this constant and maybe set it equal to maybe capital A. Okay, great. And now let's see what we have. So we'll have A times, so let's see, plugging L into this, we'll have e to the I pi raised to the m minus n. So I wrote it like that for a reason. That's using exponent rules. Notice that the L cancels. And plugging minus L into that, we'll have minus e to the I pi to the n minus m, using, fairly similar calculations. Okay, but then by Euler's famous formula, e to the I pi, well, in both of these cases, is equal to minus 1. So this simply gives us that constant a, and then we'll have minus 1 to the m minus n, and then minus 1 to the n minus m. But let's notice that m minus n and n minus m have the same parity. In other words, they're both even or they're both odd. So that means those two powers of minus 1 are always the same, which means that cancels down to 0. Well, that actually gives us a really simplified way to think about this integral right here. Notice it's 2 times L if m is equal to n, and it's 0 if m is not equal to n. So putting that together, this is equal to 2 times L times this delta mn, where this delta mn is the Dirac delta symbol. So that gives us a 1 if m is equal to n and a 0 otherwise. But what effect does that have on this double sum? Well, it has the effect of collapsing it to a single sum, because the only m values that survive are the ones where m is equal to n. So that'll give us the following object. The two L's will cancel, and we'll have the sum over all integers of an bn bar. But check it out, that's exactly what we wanted to end up with over here. Okay, good. Now that we've got this, let's look at a couple of nice applications. Okay, so for our first example, which is albeit a pretty classic one, we're going to take f of x to be x squared on the interval minus pi to pi, and then we'll extend this to a periodic function with period 2 pi. So that gives us a graph that looks like this thing that I've sketched up on the right. Okay, so now let's do our calculation. You might say, well, what about the function g? Well, we'll just set f equal to g. So we'll take both of these functions to be the same here. Okay, nice. So, well, let's do it. Let's calculate our an terms, which will be 1 over 2 times pi, because 2L is equal to 2 pi here. We have the integral from minus pi up to pi of x squared e to the I nx dx. So that's what happens when all is said and done with the simplifications. So now where do we want to go from here? Well, we can integrate this fairly easily with integration by parts. So I'll use the tabular method. So let's get our table set up right here. So I'll make this left-hand column my polynomial function, and this right-hand column my complex exponential function, or really just our exponential functions. We'll take a derivative down the left-hand column and integrate or take the antiderivative down the right-hand column. That gives me a 2x here, a 2, and a 0 here. I know to stop because I've hit 0. Here I'll have minus I over n e to the I nx. There I'm using the fact that 1 over I is equal to minus I. So my next thing will be minus 1 over n squared times e to the I nx. And then finally my next one will be I over n cubed. Let's see, yeah, that's right. And then e to the I nx. So that allows me to pretty simply write down my antiderivative. Again, using the straightforward strategy where I match on these diagonals and alternate the signs. Okay, so in the end, that's going to give me a 1 over 2 times pi, and then I'll have a minus I over n times x squared, and then next will be a plus 2 over n squared times x, and then next a plus I over n cubed times, well, nothing. I need a 2 there. And then out with everything as an e to the I n x. So that's looking good. And then next up, I need to make an evaluation between, let's see, minus pi and pi. But next up, I'm gonna like maybe skip a bit of a step. This is just simple evaluation. But what happens when you plug in pi and minus pi to this term and then subtract? We'll simply get 0. And then the same thing for this term and subtract, we'll simply get 0. That has to do with those are two even functions and the way that they work along with that complex exponential. So in the end, all I have to do is plug in pi and minus pi to what's left over. Okay, so let's put all of this together. So what will I have? I'll have a 1 over n squared times pi. I'll maybe write that as pi n squared. And then I've got an x times e to the I n x. I need to evaluate that from minus pi up to pi. Okay, so in the end, I'll have 1 over pi times n squared. And then that'll give me pi times e to the I pi raised to the n. And then minus negative pi, so that's going to give me plus pi, and then an e to the I times pi raised to the negative n for the same sort of reason. But let's see, we can do the same sort of simplification that we did before. Notice that this will simply give us minus 1 to the n, and then this will give us, well, minus 1 to the negative n, but that's the same thing as minus 1 to the n. So we can bring those out and then have the pi's cancel, and that leaves us with 2 times minus 1 to the n over n squared. Now, you might look at this and say, oh, well, what if n is equal to 0, which is definitely possible over here? Well, then this doesn't work. So that means, in fact, the calculation that we've made right here only works in the case when n is not equal to 0. But that's easy to remedy because we can simply look at the case when n is equal to 0 on its own. And maybe I'll let everyone out there calculate that. It's fairly straightforward. What you'll end up with is pi squared over 3. Okay, great. Okay, so let's summarize that and then we'll take it home. Okay, so on the last board we determined that a0 is pi squared over 3 and that an was this 2 times minus 1 to the n over n squared. Now we're ready to take it home with Parseval's identity, so I've set it up here. So I'm going to start over here with this left-hand side, which is the sum over all integers of an squared. And maybe in order to see this really clearly, we're going to break this into 3 cases. So this is going to be the sum as n goes from minus infinity to minus 1 of, well, an squared. Again, that's because an and bn are the same here, and we've got just real parts, so I don't have to take the complex conjugate. That's why this turned into an squared and not something to do with the modules of a complex number. Okay, so anyway, this is going to give us 4 over n to the 4th. And then we'll have plus a0 squared, which is pi to the 4th over 9, and then plus the sum as n goes from 1 up to infinity of 4 over n to the 4th for the same reason as this over here. And then, well, what about our integral? Well, we've got 1 over 2 times pi and then the integral from minus pi to pi of f of x squared. Again, I don't need to worry about the complex conjugate for similar reasons. So that's going to give me 1 over 2 times pi. Then I've got my integral from minus pi to pi of x to the 4th dx. But now I can use some tricks. So since x to the 4th is an even function, I can change this to a 0 if I get rid of this 2, using, like I said, the evenness of the function. And then this is a straightforward integral, and what we'll do is calculate it to be pi to the 4th over 5. It's really pi to the 5th over 5, but then this 1 over pi brings that exponent down. Okay, so next up what I want to do is observe that this term in green underline is the same thing as this term in green underline, given the fact that we've got an even power of n there. So that means I can scrub one of them away if I simply add a coefficient of 2 right there. So that's going to give me the following equation. So I have 8 times the sum as n goes from 1 to infinity of 1 over n to the 4th is equal to pi to the 4th over 5 minus pi to the 4th over 9. But that can pretty easily be calculated to be 4 times pi to the 4th over 45. Again, that's pretty simple calculation. But now we can divide both sides by 8 and we get the familiar value of, well, what is in fact the zeta function evaluated at 4. And that is pi to the 4th over 90. Okay, so let's follow this up with a maybe quick sketch of another calculation. Okay, so for our next example, let's take f of x to be e to the x and do the same sort of calculation. So here we'll have a sub n, so that's going to be 1 over 2 times pi, my integral from minus pi to pi of f of x, which is e to the x times e to the I in x. But let's see, we can put that together to give us something like this. We'll have e to the 1 plus I times n times x dx. And then from there, it's a pretty simple, straightforward calculation to get us to 1 over 2 times pi. And then, well, maybe a minus 1 to the n also. I'll put that here. And then that's going to be multiplied into e to the pi minus e to the minus pi over 1 plus in. So, and that's actually going to hold for all values of n. So now let's look at the modulus of n squared, a sub n squared. In other words, a sub n times its conjugate. So that's going to give us something like this. We'll have e to the pi minus e to the minus pi quantity squared over 4 times pi squared times 1 over 1 plus n squared, just based off of the way the modulus of a complex number works. Okay, but that's going to give us this really nice identity, and that is that e to the pi minus e to the minus pi squared over 4 times pi squared times the sum as n goes over all integers of 1 over n squared plus 1. So that's going to be equal to 1 over 2 times pi, then the integral from minus pi to pi of f squared. So that's going to be e to the 2x dx. But now let's do a little bit of simplification ahead of time. We can get rid of this 1 over 2 pi here if I change this 4 pi squared to a 2 pi. And then taking this antiderivative is fairly straightforward. Plugging in the endpoints, we'll get e to the 2 pi minus e to the minus 2 pi. But that factors quite nicely to e to the pi minus e to the minus pi times e to the pi plus e to the minus pi, just using a difference of squares factorization. Now from there, we can divide both sides by e to the pi minus e to the minus pi. That's going to bring this exponent down and get rid of this term altogether. Then we can solve, if you will, for our sum. And we have the sum over all integers of 1 over n squared plus 1 is equal to, let's see, it'll be 2 times pi times e to the pi plus e to the minus pi over e to the pi minus e to the minus pi. And I think that itself is also a nice identity. Oh, and I just realized I picked up an extra 2 here because of this thing. I should have had a 1/2 here from taking the antiderivative, which that would have brought this all the way down to 2 and would have gotten rid of this 2 here. But that's just a simple miscalculation at the end. So that itself is a nice identity, which you could in fact write in terms of hyperbolic trig functions. I believe this is going to be pi, and then the hyperbolic cotangent of pi. Okay, then you can actually do this for lots of other functions and essentially make your own sum identities. So maybe some nice ones to work with are f of x equals x times e to the x gives you a nice result. Let's see, I think f of x equals sine of x and cosine of x also give you a nice result. In fact, anything like an exponential, maybe even like e to the ax or a trig function multiplied by a polynomial will give you something that's calculatable. And that's a good place to stop.